Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 11, Lesson number 8, Limits on the Accuracy of Our Models. Before we begin, let me remind you that you can find a worksheet and a homework assignment that go along with this lesson by clicking on the video's description, or by visiting our website at www.emathinstruction.com. And although you've heard me say it almost 100 times, don't forget about those QR codes at the top of every one of our worksheets. You can use your smartphone or a tablet to scan that code, and you'll be taken right to the video that goes along with that worksheet. Alright, let's jump into our lesson. The heart of our lesson we're going to get to today in the first problem, so let's take a look at it. Mia is trying to calculate the area of her closet so she can purchase wood flooring. She measures the width and length and rounds to the nearest tenth of a meter, which obviously means she doesn't live in our country, because we don't particularly use the metric system here to measure lengths, but whatever. She found the length to be 2.7 meters and the width to be 1.4 meters. Calculate the area of the rectangular floor, include proper units. Pause the video right now and do that quickly, okay? All right. Well, we may need a calculator for this, but we certainly should know how to calculate the area of a rectangle. Length times width. So we've got our 2.7 meters. We've got our 1.4 meters. Multiply them together, probably use our calculator unless we really love multiplication of decimals, and we get 3.78 square meters. All right. Letter B gets at the essence of this. So let's take a look. Letter B. Why does it not make sense to leave this? Yeah, that doesn't make any sense. So wait, let me reword this on the fly. Why does it not make sense that this sentence is written this way? No, why does it not make sense to leave this answer accurate to the nearest hundredth? Write down a proper level of precision for this area, include units. Okay? So think about that for a moment. Why does it not make sense to say that the area is 3.78 square meters? And let me be very clear, why does it not make sense to make it that precise, to take it out to the nearest hundredth? Pause the video and think about that for a moment. All right. Well, here's why. The inputs are only precise to the nearest tenth. So the area should not be precise to the nearest hundredth. In fact, we shouldn't make that answer any more precise than the inputs. So I'm going to say that the area is 3.8 square meters. This is a very important thing in science. Very, very important. Knowing what precision level, what you should round answers to when you have imprecise, i.e. not exact inputs. And we're gonna come up with a general rule on the next page, so pause the video now and write down anything you need to. All right, let's do it. Choosing your precision level. The calculation of an output to a model should be rounded to the level of accuracy of the least accurate input to the model, or the least precise input to the model. All right, and I know precision and accuracy are a bit different. We're not going to really distinguish between them very much today. But the plain fact is, whenever we put things into an equation or into a mathematical structure, and those things that have been put in have been rounded, we should never have a final answer that's rounded to more decimal places than what our least accurate answer is. So if our least accurate answer has been rounded to the nearest tenth, then our answer should be to the nearest tenth. If the least accurate is to the nearest hundredth, then the final one should be to the nearest hundredth. And that's all we're going to be working with today. It's actually pretty easy. So let's jump into the next problem. All right, this affects us everywhere. For instance, exercise number 2. The weight of newborns for a day were recorded at a local hospital. The weights were rounded to the nearest tenth of a pound. They are as follows. So in other words, you had newborns, babies. One of them was 6.2 pounds, 8.4 pounds, 5.6 pounds, 10.1 pounds, etc. But all of these have been rounded to the nearest tenth of a pound. It says calculate the mean and the standard deviation for this data set, include appropriate units for both results, and round to appropriate levels of accuracy. All right, fair enough. Well, what we would do in this situation is we would do it all completely on our calculator. So let's do that one more time. We didn't do it that much back in the statistics unit. Let's bring open the TI-84 Plus. All right, there it is. Let's put this in to our statistics. So hit the Stat button. All right, go into Edit. If there's anything in L1, go up there, highlight L1, hit the Clear button. Remember, don't hit the Delete button. All right, clear out that data, and now let's enter it. 6.2, 8.4, 5.6, 10.1, 7.4, 8.7, 9.3, 6.8, and 7.5. All right, check over the data, let you catch up, make sure it's all in there correctly. All right, excellent. So now what we're going to do is we're going to hit the Stat button again. We're going to go over to Calculate, and then we're going to choose that one var statistics. Okay, so hit Enter. And then I want to make sure I tell it to do the one variable statistics on L1. So I'm going to have one var statistics, then I'm going to hit second one, and that's going to get me L1. And now I'm going to hit Enter. Now the mean is the mean is the mean. So as I look at my screen, I see that the mean is 7.777, etc. All right. Now what should I round to? Well, all of these things have been rounded to the nearest tenth. So that is exactly what I should round my mean to. The problem shouldn't need to tell me what to round to because I've got this general principle. If the inputs have been rounded to the nearest tenth, the outputs should be. Now, the standard deviation. That one's kind of a good question, isn't it? Should I use the sample standard deviation? Should I use the population standard deviation? Believe it or not, I think this is actually open to debate. You know, you might think that nothing in mathematics is open to debate, but I think this actually is. I'm going to use the population standard deviation because it says the weights of newborns for a day. In other words, this is the entire population of newborns that were born that day. Now, your teacher may insist that you use the sample standard deviation. Go with whatever they tell you. It's not really the point of the lesson. You know, the point of the lesson here is to look at this standard deviation, 1.388, etc., and say, well, that's a calculation based on a bunch of inputs that have been rounded to the nearest tenth, so that should be rounded to the nearest tenth. All right? That's the point. So I'm going to clear this out, pause the video now. All right. And let's get rid of that TI-84 Plus. And it's gone. I love that. It's like magic. Okay, let's go on to the next problem. Number 3. Jonathan knows that if a projectile is fired from a height of exactly 3 meters above the ground at an initial speed of 24 meters per second, then its height, h, in meters above the ground after t seconds will be given by the following formula. All right. Jonathan starts a timer and takes a picture at a time when the ball is in the air. The picture records the time signature, i.e., when the picture was taken, to be 1.7 seconds after it was launched, rounded to the nearest tenth of a second. Use the function above to determine the height of the projectile at 1.7 seconds. Do not round your answer. So why don't you go ahead and do that? That should be relatively quick, but pause the video if you need to. All right, well, let's do it. Again, I'm going to actually use function notation here because I think it's very helpful. So I'm going to put in 1.7 for t. All right, just a little order of operations. Man, have we come far. Now we're just taking random quadratic models, plugging it in. This is kind of ugly to write out in any other way. You could enter that exactly that way into the calculator, and what we would see is something pretty ugly, 29.639 meters. Now, letter B asks, why should Jonathan not report the height of the projectile to the level of accuracy given in A? What should be the proper answer with units? Well, think about that for a second. Well, now this might also be debatable, but there's one thing for certain. The input, t equals 1.7, has been rounded to the nearest tenth. All right, and because of that, we should not have our output rounded to anything more accurate. So I'm going to say my output should be 29.6 meters. All right. Now again, I think there's still some open debate here. What about the 24? What about the 3? Are they inputs or are they exact? The problem implies that the 3 is exact, but really, could it be exact? And what about that 24? Anyhow, if we're not told about rounding, then I would assume that all of those parameters are exact, even though that may not be very realistic. Okay, we're going to clear this out, so write down anything you need to. Okay, here it goes. All right, let's take a look at exercise 4. Water control engineers are keeping track of the volume of water in a local storage facility. They measure the initial amount of water to be 362 gallons to the nearest gallon. Ooh, look at that, rounding, right? Water is being withdrawn at a rate of 12.8 gallons per minute to the nearest tenth of a gallon per minute, rounding. Write a formula for the volume of water V left in the reservoir as a function of time t in minutes that the water has been draining. All right, pause the video and think about this for a moment. All right, well, here we go. This is actually a nice linear model. So what we've got is V is equal to, well, we start with 362 gallons, and then for every minute that passes, we subtract off 12.8 gallons. So there it is. In more of a traditional linear model, it might look like this, negative 12.8 t plus 362. I really kind of like it like this because it shows us the value we start at, and it shows us that we're then subtracting off. But whichever one. Letter B. Engineers would like to know how much water is in the reservoir at 7 minutes. Determine the volume and use an appropriate level of precision. So go ahead. All right, let's go through it. Well, V of 7, I'm going to use that first one, will be 362 minus 12.8 times 7. All right, and that is going to be 362. Again, you could do this all at once, but that'll be 89.6. And that's 272.4 gallons. Now, is that what we want to leave it to? Well, we had two things rounded here. The initial volume, which was rounded to the nearest integer, no decimal places, and the rate, which was rounded to the nearest tenth. So do we leave it to the nearest tenth, or do we go to the nearest integer? Well, remember, the general rule of thumb is that we should round our final answer to the level of accuracy or the level of precision of the least precise input. And the least precise input is this guy. So we should round to the nearest integer, 272 gallons. All right. Great. Let's clear this out and do one more exercise. Whoops, I'm sorry, I didn't let you hang out on that for very long. Hopefully you can rewind the video if you need to. All right, let's move on to the last problem. Exercise 5. A radioactive material decays such that 5% of it is lost every hour. They don't mention any rounding there. Scientists take a small portion of the material and weigh it to be 24.8 grams to the nearest tenth of a gram. There's some rounding. This has been rounded. Develop an exponential formula in the form A equals little a times b to the t for the amount of material still radioactive after t hours. Then use your model to determine the amount still radioactive after 10.0 hours. All right, why don't you go ahead and pause the video and attempt this problem. All right, well, let's first model it. Well, remember, when we have a model like a times b to the t, right? A represents the initial amount. And the initial amount here is 24.8. B represents, if you will, right, the multiplier. Now, we are decaying here. We're losing 5% per hour. So the B is actually going to be 1 minus 0.05 or 0.95. So the amount of radioactive material that's left is going to be that initial amount, 24.8, times 0.95. It's like we have 95% remaining after each hour that goes by. So there's our amount. And now, if we want to know how much is there after 10.0 hours, we have 24.8 times 0.95 to the 10.0. This we have to do on our calculator, and it's going to be messy. It's going to come out to be 14.848, etc. And then the question is, what do we round to? Well, the only thing that they really mentioned was rounded was this original amount of material, 24.8 grams. So that is the least precise measurement. Now, this also appears to be rounded to the nearest tenth, so that kind of all fits. So we should round our final answer to 14.8 grams. All right, so that problem was nice. It gave us a little bit of review in terms of exponential models that are decreasing. We hadn't seen one of those for quite some time. All right, and it got to that idea of rounding to the least precise level. All right, I'm going to be clearing out this text, so pause the video now. I'll give you a chance this time and copy down anything you need. All right, here it goes. Let's wrap it up. So today we saw that when we develop a mathematical model, whatever it is, the calculation of area of a garden, the calculation of the amount of water in a tank or the amount of radioactive material left, that we always have to pay attention to the precision of our inputs. And we always want to round our prediction, our model's prediction, so that it is not any more accurate than the least accurate input. Okay? Now, that being said, this is the last lesson in the Common Core Algebra 1 curriculum. So I want to thank you, not just for joining me for this lesson, but hopefully for joining me for many of the lessons. I know that they weren't always perfect. I know that I made a lot of mistakes here and there were a lot of typos in the text. Occasionally the software booted me out. Occasionally I ran out of memory on the computer. Then you had the weird thing going on sometimes where I would look a little blue, then I would change to be orange, then blue again. Really rather weird, right? That's because I don't quite have the lighting right on my studio yet. My studio. Of course, there were other things like sometimes I was in front of a red curtain, sometimes I was in front of a blue background, sometimes I was in front of my 6-year-old daughter's curtains. And then I found felt, the blue felt, and the red shirt. Right? Trust me, I do own more than one shirt. Anyhow, overall, I hope that these videos were helpful for you. Hopefully this isn't the first one you watch, otherwise you might be a little bit confused about what I'm even talking about. But like all teachers, I make mistakes. and I roll with them. So I didn't want the videos to be perfect. Or maybe that's just an excuse for them not being perfect. You can make your call. It doesn't really matter. Again, thank you. Thank you for joining me for Common Core Algebra 1. My name is Kirk Weiler. Until I see you next time, keep thinking and keep solving problems.